Thank you so much, Professor Rezzolla, for your really interesting and astonishing presentation and information that you've given us. And we have several questions about your research. The first one, could you please tell us a short about the black hole?
Okay, so black holes are the champions of gravity. If you think about gravity, where is gravity the strongest, then there is no doubt, it's black holes. So black holes are produced when a bit of matter is put into a very small volume. Any amount of matter can produce a black hole, but it has to be placed in a very small volume. So imagine all of the matter on the Earth put into a sphere of 1.5 millimeter, and then you produce a black hole out of the Earth. Okay? So that's the trick. You want to condense matter into a very small region. And I say matter, but I can also say energy, because Einstein clarified that matter and energy are the same. So you can put a very small amount of energy or matter into a very small volume, and you produce a black hole. And a black hole is the champion of gravity, the strongest gravity possible. And it's so strong that it has a surface, which is not a real surface, it's a mathematical surface, where even light cannot escape. So you can send light from outside of this surface, but if you are inside of this surface, you cannot send any more light. So it's a one-way membrane.
Thank you so much for your answer, Professor. So next question is, could you share us your opinion how they are formed and how get information from them?
So black holes are very simple objects in the sense that they are not described by many properties. In fact, they are described just by three properties: mass, spin, so how much they rotate, and charge, electrical charge. But we think that the electrical charge is always zero in astrophysics. So it's really just two numbers. And if we neglect the spin, the only relevant number is the mass. So you can take big black holes and small black holes. In practice, we think nature produces just two classes of black holes, what we call stellar mass black holes, which have a mass between 10 and maybe 50 solar masses, that's the mass of the sun, and then there are the supermassive black holes. These have masses that go from 1 million to maybe 10 billion solar masses, and these are the very big black holes at the center of galaxies. How do you form them? Well, it's a different story for different masses. For stellar mass black holes, we think they produce at the end of a life of a very massive stars. Very massive stars are like superstars. They are very active, they burn very quickly all of their money or their energy, and when they end their life, they explode. And as a result of this explosion, they normally leave a small black hole behind. So these are stellar mass black holes. Supermassive black holes, we don't really know.
How do time and space change near these holes?
Okay, so this is a difficult question to answer. If I add, equations, I could explain this very easily because it's very transparent from the equations. But the equations are, really for experts because they are difficult to understand. But if you want to have an idea, an intuition about how space and time change near a black hole, let's start with space. And space near a black hole is curved. What does it mean? Imagine a surface like a bed sheet, for instance, a newly done bed. Then the sheet is flat, everything is flat. We call that a flat space-time or a zero curvature space-time. Now imagine to put something onto it, like a heavy object, a stone, then the sheet will no longer be flat, it will be curved. And so you can think that the presence of the stone deforms the sheet. And in the same way, the presence of a black hole deforms the space around it, and actually deforms the space-time, not only the space, but also the time. And as a result of this, light doesn't move anymore on straight lines as in flat space-time, but actually does very strange trajectories. And time also does strange things. In particular, time depends on position. And if you are close to a black hole, time goes very, very slowly. So if you and I were close to a black hole, and you were closer to the black hole than me, I would become older much quicker than you, because time for you passes more slowly.
I see. Very interesting.
It's bizarre, but that's, how relativity works. And you may think this is just unbelievable. But I can show you, not without doing with a black hole, but suppose you stay here and I go on the top of this building.
Okay.
And both of us have very precise clocks. Your clock will be slower than my clock. The reason is that you are in a deeper gravitational field than I am. Oops, sorry. And so time, the fact that time depends on position, that seems so strange for us. Actually, it's true. It works. And I'll give you another example that this is true. You probably used Google Maps.
Yes, of course.
Google Maps tells you where to go and tells you your position. And it's using actually a set of satellites which are in a network which is called GPS. Now, this means that there are stations on Earth that get your signal, then they send it to the satellite. A number of satellites know where you are and tell you exactly your position. For doing this, you need to calculate what is the time that is taken from where you are to the satellite and back. But the satellite and you are on different gravitational fields. That means that the time on Earth and the time on the satellite is different. And if you don't take this into account, you would not be able to use the GPS. So every time you're using Google Maps, you're using the fact that time depends on position.
I see. Interesting. Thank you so much. In general, what are concepts of space and time of modern science? From your own knowledge, what do you think?
Well, it's a new way of thinking about things, and in particular of thinking about gravity. So what Einstein says is that there is no distinction between space and time. We tend to think that they are different, right? Because we normally move in space and we see things change in time. But if you look at the equations don't make this distinction. Time and space are just two different coordinates. And so it's a very different way of thinking about, everything happening in nature, and makes the equations much more elegant. So it's a profound result of general relativity that we should not talk about space and time. In fact, in relativity, we talk about space-time as a single word, because it's a single concept.
I see. Are there any other cosmic bodies like the black holes?
So we said that black holes are the champions, gold medal, but there is a silver medal which is maybe even more interesting, and these are neutron stars. So neutron stars can have a gravitational field which is almost as strong as that of a black hole, but they are made of matter. The same matter, the same protons and neutrons and electrons that make you or make me, you can make a neutron star. And these are fantastic objects. They are also produced by stars, and they are very small. So they have a diameter of only 20 kilometers. So imagine something like the city of Tashkent. But in the city of Tashkent, you can concentrate all of the mass of the solar system. So they are extremely marvelous objects. All the physics we know gets wild in these objects. There are extreme temperature, extreme magnetic fields, extreme gravity. If you and I were now on the surface of a neutron star, we would be completely squeezed by the gravity, because the gravity is so intense that, it would squeeze us to sheets of molecules.
I see. Could you please explain about supernova a little bit clearly?
Okay.
Like in simple words that ordinary people also could understand.
Well, I'm not sure I'll manage, but so stars have to fight gravity, because gravity wants to compress all of the stars into a single point. And the way they do this is by creating energy, by releasing energy. And this happens through nuclear reaction, thermonuclear reactions. So thermonuclear reaction produces energy, this energy produces pressure, and so a star can avoid collapsing. And this is really a burning. You burn elements into new elements, and these new elements then are burned into new other elements, and so on and so forth. But there is a limit. Once you reach that the core, the central part of a star, is all made of iron, you cannot produce energy by burning iron. At that point, the star doesn't have any other option. There is nothing it can do to fight against gravity. That's when gravity wins. And so the core of the star, this nucleus of iron, will squeeze. And will squeeze going from a size of 10,000 kilometers to just about 10 kilometers. But when it is so small, maybe it is compressed to a sufficiently large pressure that the star says, no, I can stop here because now I have enough pressure to fight against gravity. And so you have to imagine this thing will collapse, and then at one point it will stop. But there is still all the rest of the star that is still falling, and then all of a sudden finds a hard surface, like a wall. And so what it does is it hits the wall and then bounces back. That's an explosion. And we see that explosion in terms of supernova. So a supernova is a star that is no longer able to produce energy. It is collapsing, but at one point stops, creating a wall for all the rest of the star. And when that happens, the star just explodes.
I see. I see. Thank you so much, Professor. Actually, all this question was from our professor.
Okay.
Yeah.
Okay.
His name is Professor Laziz, and
Doctor of Philosophy.
Yeah, Doctor of Philosophy, and these are special for his own channel,
Okay.
Science, and I'm just helping him to translating.
Okay.
And also, he mentioned he has a couple of questions.
Okay.
And